Find the Taylor series of the function 1 over x squared about a equals 3. Since it is a Taylor series, we have to create this from scratch. No building blocks can be used. So I start off with, let's look at our function and take some derivatives. I want to think about this as x to the minus 2. Our first derivative, that's minus 2, x to the minus 3. Second derivative, pull down the negative 3, so that is going to be a 2 times 3, x to the minus 4. Now once again, do not simplify the constants other than the negative sign. The third derivative, that's minus 2 times 3 times 4, x to the minus 5. And the last derivative I'll do is the fourth derivative. And that is 2 times 3 times 4 times 5, x to the minus 6. Now, in all of these, I can look at them as a fraction. So this is minus 2 over x cubed. This one is 2 times 3 over x to the fourth. The third derivative is negative 2 times 3 times 4. Over x to the fifth, and the fourth derivative is 2 times 3 times 4 times 5 over x to the sixth. Now we look and say, can I find the nth derivative? Can I find that formula? And we try to do this in parts and pieces. In other words, let's work through it one step at a time. I notice, first of all, there's an alternating sign. So the first and third derivative are both negative. The second and the fourth derivative are both positive. Our original function is positive, so this is going to give me a minus 1 to the, well, to the n. When you talk about the first derivative, when n is 1, that's negative. When n is 2, that's going to be minus 1 squared, that's positive, so I now have the sign taken care of. I look at the fourth derivative and say, you notice there's a 2, 3, 4, 5. The third derivative had a 2, 3, 4. The second derivative had a 2 and a 3. So this looks like it's a n plus 1 factorial. Now normally a factorial multiplies all the way down to 1. We're missing the times 1, but times 1 doesn't change anything, so that's not a problem. So notice the fourth derivative, the highest coefficient there is a 5. The highest number there is a 5, so that's my n plus 1 factorial. Now my power on x, I look in the fourth derivative, the power is a 6. The third derivative, the power is a 5. The second derivative, the power is a 4. So this is going to be n plus 2. So now I have a formula for the nth derivative. And the question we want to ask is, does it work for all n? i.e. n greater than or equal to 0. Because when n is equal to 0, that's the original function. So if you think about it, let's just look at when n is 1, that's minus 1 to the first, so that's negative. 1 plus 1 is 2, factorial, so that's a 2. x2 cubed, so it's x cubed. So it works for n equals 1. And I could check it on any of the later values of n. But the big thing I want to be careful about, does it work for n equals 0? So when n equals 0, that is the original function. That is our function that we start with. So when n equals 0, minus 1 to the 0, that's 1. 0 plus 1, that's 1 factorial. 1 factorial is 1. X to the 0 plus 2, that's x squared. And the answer is yes. So at this stage, I don't have to do any adjustments for the values of n. The next example, you'll see we'll have to make an adjustment. For this one, we're good. So now I have the formula for the nth derivative. Why do I want this? Because c sub n, which is our coefficient for the Taylor series, is the nth derivative at a divided by n factorial. So in our problem here, we know that c sub n is going to be the nth derivative at 3 divided by n factorial. And if we look at this, this becomes, I'm going to write this as a 1 over n factorial out front. And the reason I do that is because my nth derivative is already a fraction. Minus 1 to the n plus 1 factorial, x to the power. So this is going to give me a minus 1 to the n plus 1 factorial. And this is 3, because 3 is our x value, to the n plus 2. So we're plugging in that number for our x. Now let's clean this up. We see that there is a n factorial and n plus 1 factorial. We've seen how these cancel in the previous section. So this is minus 1 to the n times n plus 1 over 3 to the n plus 2. So now we have the coefficient formula. We have c sub n. Thing to remember is every Taylor series is a summation c sub n equals 0 to infinity, x minus a to the n. That is our general formula for our Taylor series. So for this one right here, we see that this is going to be a summation n equals 0. Our c sub n is minus 1 to the n plus 1, 3 to the n plus 2, and don't forget the x minus 3 to the n. A lot of students will forget that last bit. And so there is our series, which is equivalent to 1 over x squared. Now, of course, it's equivalent to that while you're inside the radius of convergence. Now, if you look back to the problem, it just asked me to find the Taylor series. If you wanted to know the radius of convergence, you would now do the ratio test on this, and then you could talk about the radius of convergence. And thus, you can talk about the interval of convergence. But that's all we wanted for this problem. Find the Taylor series for this function about a equals 2. So it's a Taylor series, so it means we start from the beginning and work our way through all the derivatives. So f of x is natural log of x. F prime is going to be 1 over x, or x to the minus 1. The second derivative is minus x to the minus 2. The third derivative is going to be 2x to the minus 3. The fourth derivative is going to be a minus 2 times 3x to the minus 4. And the fifth derivative is going to be 2 times 3 times 4x to the minus 5. Now, once I get to here, I see enough that I can sort of catch where the factorials are. So once again, don't multiply out the constants. You tend to lose the pattern when you do that. Now, the nth derivative formula is what we're looking for. So I first of all notice that there is an alternating sign. So there's minus 1 to a power. Well, our second derivative is negative. Our fourth derivative is negative. The first, third, and fifth derivative are all positive. So let's make this n plus 1. I noticed that my x to a power, while I wrote it x to the minus 5, minus 4, minus 3 into the formulas, that was to make the derivative easier. So pull the x to the minus 5 to the bottom, that becomes x to the fifth. The fifth derivative has a fifth, so that is x to the n. And now I look at the constants. Well, the fifth derivative has a 4, 3, 2. It's missing the 1 to give it a 4 factorial. But multiplying by 1 doesn't change anything, so dividing by 1 doesn't change anything. So even though it's missing that 1, it's still a n minus 1 factorial. So there is our formula for the nth derivative. Now we ask the same question, does this work for all n values? Now, if you look at n equals 5, minus 1 to the 6, that's positive. 5 minus 1 is 4 factorial, x to the 5, it works for 5. And you can quickly check for 4, 3, 2, and 1. If you plug in a 1, minus 1 squared is positive. 1 minus 1 is 0 factorial. And guys, remember 0 factorial is defined to be 1. And x to the 1 is here. And the answer is yes, if n is greater than or equal to 1. As long as n is some integer greater than or equal to 1, the answer is yes. If n is equal to 0, then the answer is no. Now, what does n equals 0 represent? N equals 0 represents the original function. So we have an issue here. If n is 0, I don't get my function. So I'm going to have to deal with that, and I will deal with that later on in the process. But if you think about it, our derivative, our nth derivative formula, there's nothing you can plug in for n that will simplify out to a natural log. So there is our formula. Why do we want that? Because the general formula for the coefficient is c sub n. This is the nth derivative at where we're centered over n factorial. Now, where are we centered? I'll scroll back to the top. We're centered at 2. So come back here. So it's the nth derivative at 2 over n factorial. So this is going to give me a 1 over n factorial times, this is a minus 1 to the n plus 1, n minus 1 factorial over 2 to the n. So I go back to my nth derivative formula, my minus 1 to the n plus 1, n minus 1 factorial. I'm replacing this 2 in for my variable x. And I have the 1 over n factorial for my formula c sub n. So scroll back down and say, okay, let's simplify. Now this is going to give me a minus 1 to the n plus 1. If I do it in steps, this would be n minus 1 factorial. My n factorial is n times n minus 1 factorial, 2 to the n. We see our n minus 1 factorials cancel. And I have this is equal to minus 1 to the n plus 1 over n, 2 to the n. And this is true as long as n is not equal to 0. So this is a very big if right here. Now, our series, our Taylor series is the summation n equals 0, c sub n, x minus 2 to the n. This is x minus a. We're centered at 2, so we have x minus 2 there. And this is the general form for n equals 0 on. But the problem is n equals 0 has a problem. So I really need to think about c sub 0 separately. When n equals 0, this is c sub 0. X minus 2 to the 0, that's a 1. And this summation now will start off at 1, c sub n, x minus 2 to the n. So I take off the first term. Now, what is c sub 0? Now, I'll write out the rest of this real quickly, because the rest of it's easy to write out. We found our formula for c sub n. This is minus 1 to the n plus 1 over n 2 to the n. This is x minus 2 to the n. So that's what I have. The only thing I don't have is c sub 0. And so we look and say, well, what is c sub 0? Well, that is the 0th derivative at 2 divided by 0 factorial, which basically means this is f of 2. Now remember, our function was natural log of x. So f of 2 is equal to natural log of 2. And so I find that c sub 0 is that value, which means this is natural log of 2 right there. So it's just like when we did the power series, the rule for natural log of 1 plus x, we had that constant that we had to solve for, and that's what's that natural log of 2 is coming from. And so I find that my natural log of x as a Taylor series centered at 2 is equal to the natural log of 2 plus that summation. So for a real quick recap, I start the problem off saying Taylor series, find the derivatives. I find the pattern of the derivatives. In this case, I recognize the pattern works for every n value bigger than 1 and bigger. It doesn't work for n equals 0. I take my c sub n, which is my nth derivative divided by n factorial, evaluated at x equals 2, simplify that down, once again reminding myself that it doesn't work for n equals 0. I take my general formula. I take off the first term, the n equals 0 term, and then the rest of it from n equals 1 to infinity is still that summation. Substitute my c sub n. And then look at this thing and say, okay, what's C0? C0 is the original function divided by 0 factorial, which is 1. So it's the original function at our x value. So that is our natural log of 2.